Hey everyone, welcome back to another video. In this video, I'm going to be solving several challenging time value of money practice problems. What I recommend you do is at the start of every question, pause the video and try to solve them yourself. Then watch me go through it. In the first half of the video, I'll be solving the questions using formulas. In the second part of the video, I'll be solving the same questions using the financial calculator. I recommend watching the entire thing because even if you're using a financial calculator, understanding how to do it with the formulas really gives you a solid foundation. And before we start, please go ahead and subscribe to the channel as it is the best way to support me and my desire to bring high quality, easy to consume tutorials to you at no cost. Okay, so John has to choose between two investments that have the same cost today. Both investments will ultimately pay $1,300 but at different times as shown in the table below. If John does not choose one of the investments, he could leave the funds in a bank account paying 5% per year. Which investment should John choose? Okay, so the first thing I'm seeing here is they've given you the discount rate here. It said if he doesn't invest, he can put his money in a bank account that's basically an opportunity cost, which in TVM we can use as a discount rate. So we're going to evaluate these two investments at a 5% discount rate. All you need to do to solve a question like this is find the present value of the two investments and compare them. So I'm going to start with investment A. It's going to receive nothing in the first year, 500 in the second, 800 in the third. So the present value today, so PV0, going to discount the 500 at 5%, so divided by 1 plus 0.05 to the power 2, right? I'm discounting back 2 years. And then the second one, I'll discount that back by 3 years. So 1 plus 0.05 to the power 3. So this one has a present value of 1,144.58. For investment B, same idea. But this time there is a payment in year one, so this one will be discounted at 5% for 1 year. Then $400 in the second year would be discounted by 5% for 2 years. And finally, the same thing, $700 discounted at 5% for 3 years. So between the two, investment B has a slightly higher present value, and therefore John should choose that one. A company just declared that its dividend next year will be $4 per share. That rate of payment will continue for an additional 3 years. I'm going to start a timeline here. So next year, $4. And then an additional 3 years. So 1, 2, 3 more years, it'll continue at $4. After which the dividends will fall back to their usual $3 per share. So after that, the dividends will continue at $3. They don't say when they'll stop, so we can assume that they'll continue forever. What is the present value of all future dividends given a discount rate of 12%? Okay, so we've got a two-parter here. We've got a perpetuity at the end and an annuity at the beginning. So I'm going to start right to left since I'm looking for the present value. And I'll start with my perpetuity, which is right here. The present value of the perpetuity is 3, the payment, divided by the discount rate. So that's $25. And this would be PV. If I look at my timeline and I add just some timestamps here, this is PV4. The payments are at time 3, and I'm treating this as an ordinary perpetuity, meaning that the present value would be 1 period before the start of the payment. So this is the value in 4 years. Okay, so now this will become the future value for the next step. So if I want to take that number now and bring it back to time 0, I'm simply going to discount it at 12% for 4 years. So I get $15.89. Okay, so we've completed half the question. We've solved for half the timeline. Let's work with the annuity now. For this one, I'm going to use my ordinary annuity formula. So the payment is 4. I multiply it by 1 minus 1 plus the discount rate to the power negative n. So negative 4 in this case, since there are 4 payments, divided by 0.12. And for this, I get a present value of 12.15. And this is a present value at time 0 since the payments began at time 1. Last step would simply be to add the two together. So the present value of the first 4 payments plus the present value of the remaining payments would give me the total value of this investment, just $28.04. After living in a university residence for 1 year, Carla decides to rent an apartment for the remaining 3 years of her degree. She has found a nice location that will cost $550 per month. Rent for the first and last month must be paid up front. How much money would Carla need to have in her bank account right now to be sure she will always have enough for rent? The bank account pays 4.5% interest, compounded monthly. Okay, so you've got an annuity, but with a small twist where the first and last month's rent are due up front. So rent in general is due at the beginning of a period. So when I'm reading this question, that's the first thing that kind of jumps out at me. This is an annuity-due because rent is paid at the beginning of the month. But I like timelines, so I'm going to draw a timeline. It's $550 per month. She has to pay the first month's today. So we'll call that time 0. And this is for 3 years. So on my timeline, basically this would continue until 36. But the last payment would normally be at the beginning of the 36th month, which is here. So this is what it would look like normally. Like if she didn't have to pay the first and last month's rent at the beginning, and she just had to pay the beginning of each month. But because they said the last month's rent has to be paid at the beginning, this amount would get moved to the start. So the timeline would actually look something like this. You would have your initial payment here at time 0, and then you have another one at time 1, another one at time 2. That would basically continue, and the last payment would be made at time 34, which is the beginning of the 35th month. There'd be no payments after that. But there would also be an additional $550 at the start. So this is what it looks like on a timeline. You have 35 payments of $550 all made at the beginning of each month. Plus you have an additional $550 paid at the start. So best way to do this would be to deal with the 35 payments as an annuity and then just add on the extra payment in the final step. So this is what that would look like. $550 is my payment, multiplied by 1 minus 1 plus the discount rate, which is 4.5% compounded monthly. So my 4.5% divided by 12. And then the n would be 35. Again, I'm not accounting for that last month that got moved to the start, right? I'm kind of ignoring that for now. We'll divide that by the rate. So that divided by 12. So this is the formula if this were an ordinary annuity. But because this is an annuity-due, we're going to multiply this by 1 plus the discount rate, which is 0.045 divided by 12. And this is going to give me the present value today of those $550 payments for 35 months. Once I've calculated that, then I'll just add that 36th payment that they're expecting from us at the beginning. So I'll deal with the annuity, and then I'll add on that $550. So the answer here is $18,626.17. A 65-year-old man intends to use his retirement funds to purchase an annuity from a life insurance company. Given the amount of money that the man has available to invest, the insurance company is able to offer 2 alternatives. The first option is to receive $2,785 each month for as long as he lives. The second option is to receive $3,500 each month, but only for 20 years. Payments will be made to his estate if he should die before that time. The relevant interest rate is 6% per year, compounding monthly. How long must the man live for the first option to be the better deal? Okay, so we have here two options. One of them is to get paid $2,785 for as long as he lives. So they're both annuities. So that is also an annuity because it's not going to go on forever. It's only going to go on for as long as he lives. So it's an annuity, but we don't know when it's going to end. And the other one is $3,500 per month for 20 years. So that one we know is an annuity for 20 years. They've asked you at what point would the first option be the better deal? Now, in questions like this, when you're looking for, whenever they ask when would one deal be better or when should he choose one over the other, you generally want to look for the point where they would be the same. So really this question is asking you, how long must he live for both options to have the same value? So what I would start by doing here is finding the present value of the annuity that we have all the information for, and that is the second option. So if I look at that second option, it is $3,500 each month for 20 years. So that would be a payment of $3,500. I'm going to find the present value of this annuity using the ordinary annuity formula. So 1 minus 1 plus the discount rate of 6% compounded monthly. So that would be 6% divided by 12. And it's monthly payments for 20 years. So we would have 240 payments. So I'll put that to the power of 240. That is 12 payments per year for 20 years. All that divided by the rate, which is again 0.06 divided by 12. And you should get $488,532.70. So that is the present value of the second option. Next, we're going to take that value and plug it in as the present value of the first alternative, but this time we'll be solving for n. So 488,532.70, and the payment is $2,785. Same formula, same interest rate, but n is the unknown. So I'll just leave that as an unknown. Okay. Now, if you're using a financial calculator, this question is much easier because you could just punch everything in and have the calculator do the work. If you're solving this using the formula, we're going to do the algebra. So let's start by dividing both sides by 2,785. That'll get rid of that one. So now to avoid rounding, I'm just going to keep everything as a fraction for now. So I have 488,532.70 divided by 2,785. And I'm going to multiply both sides by 0.06 divided by 12. That's trying to get rid of this denominator. So I'll multiply this by 0.06 over 12. And if I just write where I'm at, now I have just the numerator left in my work. So I'll simplify this. This is 0.005. That's 0.06 divided by 12. All that to the negative n. Okay, from here I'll punch the left side into my calculator before it gets too crazy. So 0.870785 equals 1 minus 1.005 to the negative n. From here, if we rearrange this, you'd have 1.005 to the negative n equals 1 minus the 0.877075, which is 0.1229215. And here we're going to use logs. So we'll put a log on each side, and that will allow me to carry down this exponent. So negative n times the log of 1.005 equals the log of 0.1229215. Now, if we keep cleaning this up, I would have log of 0.1229215 divided by the log of 1.005, which on the calculator would be negative 420.29. So n is 420.29. Now this is in months. If I divide this by 12, that would be approximately 35.02 years. So he would have to live an additional 35 years before the first alternative matches the value of the second one. And if he lives longer than 35 years, then the first alternative would actually be the better option. Two friends, Gabe and Sarah, are planning for their retirement. Both are 20 years old and plan on retiring in 40 years with $1 million each. Sarah plans on making annual deposits beginning in 1 year for a total of 40 deposits, while Gabe plans on waiting then depositing twice as much as Sarah. If both can earn 5% per year, how long can Gabe wait before he starts making his deposits? So they both want to end up with $1 million. We know that Sarah will be saving for 40 years to reach $1 million. Gabe will be depositing twice as much, but he's not going to start right away. So let's start by finding out how much Sarah will deposit each year. So we know her future value is $1 million. We know she's going to make 40 deposits. She's making annual deposits for 40 years. So if 1 million is my future value, I'm going to set that equal to the future value of an ordinary annuity formula, but I'll set my payment as the unknown. So 1 plus the discount rate to the power of 40 minus 1, all of that divided by 0.05. So if we punch this into the calculator, we'll have how much she would have to deposit every year for 40 years. So the payment here is $8,278.16. Now that we know her payments, we know Gabe's payments, because the question says that he'll deposit twice as much. So if I multiply this answer by 2, his payments would be $16,556.32. And I was saying, how long can he wait? So now we're going to be looking for time. We know his future value is $1 million. We know his payments are $16,556.32. Same interest rate, but we don't know n. So this would be a little bit similar to the previous question, where at some point we're going to have to use logs to solve the answer. But let's simplify it as much as we can. So I'm going to first start by dividing this side by the payment, $16,556.32. That'll get rid of the payment here. I'm also going to multiply it by 0.05. That will get rid of that. And then I'll take that answer and subtract 1. Or I'll add 1, excuse me. That'll get rid of that. So let's start. So I have 4.01999.478 equals 1.05 to the n. Now using the log rule, we'll log both sides, bring the n down, and we'll end up with n equals the log of 4.0199478 divided by log of 1.05. So the answer is 28.52. So what we found here is that Gabe would have to deposit 28.52 times, so 29 times, to reach $1 million. Since Sarah would have to deposit 40 times, he can actually wait. So if we take this minus 29, he can wait 11 years. As long as he starts by the 11th year, he'll be able to reach $1 million at the same time as Sarah. Amanda would like to borrow $50,000 to pay 1 year's tuition at a private U.S. university. She would like to make quarterly payments and finish repaying the loan in 5 years. If the bank is quoting her a rate of 6% compounded monthly, what is her quarterly payment? Okay, so she's borrowing $50,000. That is the present value. She's going to make quarterly payments, and her interest is compounding monthly. So we've got monthly compounding, so I call compounding M, 12, but quarterly payments. So the frequency of the payment is 4. The first thing we need to do here to find the quarterly payment is to find the quarterly rate. So to find the effective quarterly rate, we're going to take 1 plus the discount rate of 6% over the compounding to the power the compounding over the frequency minus 1. So this is your basic periodic rate formula. And that gives us a rate of 0.01508 per quarter. Okay, now it's a little bit easier. It's an ordinary annuity, since the payments are made quarterly, and it doesn't mention anywhere that the payments will be made at the beginning. So if it's not mentioned, I always assume it's at the end. We've got 5 years with quarterly payments, so N would be 20. Okay, so 50,000 is the present value. PMT is what we're looking for. 1 minus 1 plus the rate to the negative 20. All of that divided by 0.01508. So algebraically, you would get a payment of $2,914.58 per quarter. Wilma would like to borrow $250,000 to start her own business. She would like to make monthly payments to repay the loan in 10 years. The bank is quoting her a rate of 6% compounded quarterly. Determine the monthly payment. So this is kind of the opposite of the previous question. This time, the compounding, so M is quarterly, but the payment frequency is monthly. So in this case, you're going to need an effective monthly rate, but we're going to use the same formula. So 1 plus the nominal rate of 6% divided by the compounding divided by, to the power 4 over 12 minus 1. And for this, you should get a monthly rate of 0.004975. So using an ordinary annuity formula, once again, we're going to be solving for the payment. So the present value is $250. That is the amount that was borrowed. PMT is what you're looking for. 1 minus 1 plus the rate you found. Now for N is 10 years with monthly payments. So N is 120. So to the power negative 120 over the rate. So here the monthly payment is $2,771.75. Margot has designed a new car that will cost $80,000. He has $25,000 in his savings. earning interest at a rate of 0.5% per month. How long to the nearest month will it be before he can buy the car? Okay, so this is a lump sum question. He's got $25,000 today. He earns 5% per month, or excuse me, 0.5% per month. How long will it take to reach 80,000? So 80,000 is the future value. 25,000 is the present value. So I'm using the basic future value formula. I'm going to multiply this by 1 plus 0.005. That is 0.5%. 0.5% is 0.005 in decimal form. And we're looking for n. How many months will it take if he's earning 0.5% per month to grow 25,000 to 80,000? So if I divide both sides by 25,000, so if I divide this by 25,000 to get rid of that, I have 3.2. So 3.2 equals 1.005 to the n. Now we'll log both sides. So n would be log of 3.2 divided by log of 1.005. So for part B, you would need a financial calculator because the algebra would be too much to do manually. The idea here is you've got a present value of 25,000. And you have payments of $300. The interest rate is 0.5. And the future value is 80,000. Now for the financial calculator, you're going to want to make the future value negative. The idea here is the 25,000 and the 300 are both going into the savings account, but the 80,000 will come out of the savings account and be spent. So the cash flows are moving in opposite directions. The calculator should know that. And then you want to compute. So on your calculator, you're going to want to make sure that your PY and CY are both set to 1, since we're not trying to use them in this case. And if you've been using them for other things, like if I press second IY, you can see that both of these are both set to 1. For this, you should get approximately 100 months. How many years will it take for an investment to double in value if the rate of return is 9% and compounding occurs A annually, B quarterly? Okay, so we're looking for how long it'll take to double your money at 9%. We're going to set our present value to 1 and our future value to 2. And just use the basic future value formula. So 2 equals 1 times 1 plus the rate. So at annual compounding, I'm just going to leave my n, my rate as 9%, and I'll put that to the power n. So if I were to simplify this, I would end up with 2 equals 1.09 to the n. And you could log both sides. And your n is the log of 2 divided by the log of 1.09. So it would take 8.04 years. Now, if the compounding were quarterly, I'd basically do the same thing. So this was for A. For B, it would still be 2 equals 1 times 1 plus, but this time my rate would be divided by 4 to the n. And I would go about it in a similar way. 2 equals 1 plus 0.09 divided by 4 is 1.0225 to the n. And then once again logs. So log 2 equals log of 1.0225 to the n. N would equal log 2 divided by log of 1.0225. So n is 31.1518, but this is quarterly. So I'm going to divide this by 4 now. It would take 7.79 years. Okay, so the next part of the video will be for the students that use the financial calculator more than the formulas. So I'm going to go through these questions once again, now using only the financial calculator. So this first question, remember, it was to find the present value of each investment to decide which one was better. So for investment A, if you want to find the present value of this cash flow very quickly, so I'm going to open up the calculator and I'm going to go into cash flows. So CF. Make sure that nothing is stored there. So you see I've got numbers stored there. I'm going to press second function clear work like that. It's all set back to 0. Okay. So my cash flow at time 0, I'll leave that as 0. Then I'll go down. Cash flow at time 1. For investment A, that's also 0. So I'll leave that as it is. We'll skip over the frequency as well and go to cash flow. Now for the frequency, we're going to want to set that to 1. And basically we're telling the calculator that we have a payment of 0 one time. Then go down. Investment A has a $500 payment as the second cash flow. We'll arrow down. The frequency is 1. That's fine. We can leave it as it is. Then go down again. The third cash flow is 800. Enter. Great. Now you'll want to press net present value. I is for the interest rate. In this question, the interest rate was 5%. So 5, enter, down, and press compute. So the present value for investment A is $1,144.58. For investment B, we're going to repeat that process. Cash flow, second clear, so that we can clear everything that we had just entered. The first cash flow, so times 0 is 0. We'll always leave that as 0. Then we'll arrow down. The cash flow at time 1 is 200. So 200, enter, down. We'll leave the frequency as 1 because it's only happening once. Then the second cash flow is 400. Enter, down, leave the frequency as 1. And then 700, enter. Then just like we did before, we'll go to NPV, set the interest rate to 5, enter to save it, arrow down, compute. And for investment in B, we get a present value of $1,157.97. Company just declared that its dividends next year will be $4 per share and that payment will continue for an additional 3 years, after which the dividends will fall back to their $3 per share. The discount rate is 12%. So on a timeline, that would look like this. 4, 4, 4, 4. So $4 in 1 year and then for an additional 3 years. And then it's going to drop to 3, 3 indefinitely. The rate is 12%. So I'm going to start with my perpetual side. So here we'll set the payment to 3, the interest rate to 12. The N, we're going to set it as 9999. Basically to mimic a perpetuity. And we're going to compute the future value. And we're going to compute the present value. So 3 payment, 12 IY, 9999, and compute present value. And we get a present value of negative 25. We can ignore the negative for the most part as far as interpreting the answer. It's actually just 25. So this is PV at time 4. So again, if I were to put timestamps here, since the first payment of the perpetuity is at time 5, this is the present value at the beginning of year 5, which is year 4. Now this would become the future value for this part. So I'm going to set my future value here to 25. The payments now would be 4. The rate is 12. And the N is 4 because we have 4 payments. Compute PV. So 25 future value, 4 payment, 12 IY, 4 N, compute PV. We get a present value of 28.04. After living in a university residence for 1 year, Carla decides to rent an apartment for the remaining 3 years. She's found a nice location that will cost $550 per month. Rent for the first and last month must be paid up front. how much money would Carly need to have in her bank account right now to be sure she will always have enough for rent? The account pays 4.5% interest compounded monthly. So the way that I would solve this on a financial calculator is by first setting it to BGN, because rent is paid at the beginning of each period. Now we're going to set our payment to $550. Our interest rate is 4.5 with monthly compounding. So we're going to set the compounding to monthly and the payments per year monthly as well, because we're compounding monthly and we're paying monthly. We'll set future value to 0 since we don't really need it. And we'll set N to 35. Now the reason it's 35 is I'm ignoring the last month's rent. The reason is they're asking us to pay the last month's rent at the beginning. So there actually won't be a payment in the last month. We're going to compute the present value here. So second payment, second enter to turn on BGN. 550 is your PMT. 4.5 IY with monthly payments and monthly compounding. 0 future value, 35N compute present value. So the present value is $18,076.17. So that would be the present value of 35 months of rent. And we're going to add to that the extra payment that needs to be made at the beginning. So the answer is $18,626.17. A 65-year-old man intends to use his retirement funds to purchase an annuity from a life insurance company. Given the amount of money the man has available to invest, the insurance company is able to offer two alternatives. The first is to receive $2,785 each month for as long as he lives. The second option is to receive $3,500 each month, but only for 20 years. If the interest rate is 6% compounding monthly, how long must the man live for the first option to be the better deal? So to solve this question, we're going to basically try and figure out how long would he have to live for the present value of the first option to equal the present value of the second option. So I'm going to start by taking the second alternative, which has a payment of $3,500 for 20 years. So 20 times 12 is $240. The interest rate is 6%. It's compounding monthly, and the payments are also made monthly. Future value 0, and we're going to compute the present value for this part. So I missed a 0 here. So 3,500. Oh, it's important to turn off BGN from before. Make sure that's not on. So 3,500 PMT, 240. N, 6 IY, 12 and 12. 0 future value, compute present value. So the present value of the second option is $488,532.70. Now we're going to keep that as the present value for the second part. So this was step 1. We're going to keep that as our present value, exactly as it is, including the negative, so the calculator understands what it's doing. We're going to set the payment now to $2,785. We'll keep the rates as they are. So I'm going to write them, but you won't have to punch them in again since it's already in there. Future value 0. Compute N. So present value, we'll leave that as it is. I'm just changing the payment, really. The rates, I'm going to leave them. Future value is already there. Compute N. And I get an N of 420.289. And this is in months. So if I divide this number by 12, you would have to live 35.02 years before the first option is the better choice. Two friends, Gabe and Sarah, are planning for their retirement. Both are 20 years old and plan on retiring in 40 years with $1 million each. Sarah plans on making annual deposits beginning in 1 year, while Gabe plans on waiting and then depositing twice as much as Sarah deposits. If both can earn 5% per year, how long would Gabe have to wait? So for this one, I would start by figuring out how much Sarah is going to deposit. So we know that she's going to end up with a future value of 1 million. She's starting with nothing, so the present value is 0. The interest rate is 5%. And for this, it's important that your CY and your PY are both set to 1 because we're not trying to use them in this question. And she's making annual payments, so a PY of 1. The compounding is not mentioned, so we'll make sure that's set to 1. N is 40 because she's going to make 40 payments. Compute PMT. So 1 million future value, 0 present value, 5 IY. And I'm going to go into my IY and switch PY and CY to 1. So the fastest way is just to clear them. So second clear. See, they're both 1 now. Get out of there. 40N, compute PMT. 8,278.16. Now, since Gabe is going to invest twice as much, I'm going to multiply that by 2, and that'll be his payment. So his payment now will be 16,556.32. And we're going to make that negative for the calculator to understand that he's giving up this money so that he can get back $1 million later. His future value is also $1 million. His present value is 0. The rate is still 5%. This time we're computing N. So I'm going to set this 16,556 as my payment. $1 million is my future value, same as before. Present value, same as before. Interest rate, same as before. Compute N. Compute N. So what we calculated here is that it would take Gabe 28.52 years to reach $1 million. So since Sarah is starting now, Gabe can wait approximately 11.5 years to start saving. Amanda would like to borrow $50,000 to pay 1 year's tuition at a private U.S. university. She would like to make quarterly payments and finish paying the loan in 5 years. The loan is 6% compounded monthly. What are her quarterly payments? So for this, you're going to set the present value to 50,000. N is 20. 5 years with quarterly payments is 20 payments. Interest rate per year is 6 with monthly compounding, so CY of 12, and quarterly payments, so PY of 4. Future value 0. Compute payment. So 50,000 present value, 20N, 6IY, PY 12, excuse me, PY is 4, CY is 12, 0 future value, compute payment. $2,914.44. Wilma would like to borrow $250,000 to start her own business. She would like to make monthly payments to repay the loan in 10 years. The bank is quoting her a rate of 6% compounding quarterly. Determine her monthly payments. This is basically the exact same thing we did in the previous question. The present value is $250,000. N is 10 years with monthly payments, so 120. The interest rate per year is 6, so IY is 6. The compounding is quarterly, and the payments are monthly. Future value 0. Compute payment. So 250,000 present value, 120N, 6IY. Then we'll change our compounds and our payment frequency. So payments per year 12. Compounds per year 4. 0 future value, compute payment. Her monthly payment is $2,771.78. Marco has his eye on a new car that'll cost $80,000. He has $25,000 in savings, and his account earns 0.5% per month. How long will it take before he can buy the car? So $25,000 is your present value. Future value is $80,000. Now, you're going to want to set one of these to negative. So we're going to set the present value to negative for the calculator to understand. The interest rate is 0.5. Now we're going to set PY to 1 and CY to 1. This is because you're already given a monthly rate. So you want to make sure in this case that you're not entering PY and CY, or that you're entering them as 1. There is no payment, so payment 0, compute N. So 25,000 negative PV, 80,000 FV, 0.5 IY. We're going to clear this, make sure those are both set to 1. 0 payment, compute N. It would take him 233.2 months. So they want that rounded to the nearest month, so 233. For B, same question, but this time we're going to add a payment. So it's saying on top of the 25,000 he has, he can add $300 per month. So the present value is still negative 25,000, but we're going to add a payment of negative 300 in order to reach our future value of 80,000. Now, it doesn't actually matter which ones you make negative as long as you keep the same pattern, meaning that I can make present value and payment both positive and make future value negative, and that would give me the exact same result. The calculator just needs to know that they're going in opposite directions. Everything else would be the same. The rate is still 0.5, and we're computing N. So in this case, all I really need to do is go in and add the $300 payment, so 300 negative PMT, compute N. So I get 100.05 months, so about 100 months. How many years would it take to double your money at 9% with annual compounding and with quarterly compounding? And they want the answer in years. So for A, we're going to set our present value to -1 and our future value to +2. You can take any numbers as long as the future value is twice as much as the present value because we're trying to double it. The interest rate is 9%. We're going to set PY and CY both to 1. There is no payment. Compute N. So -1 present value, 2 future value, 9 IY. I'm going to make sure that these are both set to 1. They are. 0 payment, compute N. So it would take about 8.04 years. Now, if the compounding was quarterly, the only thing I would change is my quarterly compounding. So I'll keep my present value as -1. I'll keep my future value as 2. The IY is still 9. But this time I'll keep PY as 1, but I'm going to change my compounds to 4. Quarterly compounding. Payment 0. Compute N. So on my calculator, I'm just going to go directly to the thing I'm trying to change, which is the CY. I'm going to make that 4. Everything else is the same. I don't need to do it again. Compute N. You see that number drops a little bit to now 7.79. So that's it for this video. I hope that you found it useful. I hope you were able to follow along with my explanations. If you have any questions of your own, please leave a comment and I will respond to them. See you at the next video.